Welcome. Today, we're diving deep into hydraulic fracture propagation. We're shifting focus a bit away from pure theory and more towards real-world application.
That's right.
We'll be looking at a simulation technique, the Generalized Finite Element Method, GFM, and really seeing how it stacks up against actual lab reality.
Mm-hmm.
So our mission today is pretty straightforward. We're reviewing this really rigorous engineering study. It systematically pits this advanced GFM simulation against physical, controlled laboratory experiments.
Yeah, and these aren't just simple setups either.
No, they involve diverse fracture geometries, different fluid conditions. It's not just about coding something that runs, it's about making it predict actual physics.
And that step, the validation against physical data, that's really the crucial bit. In modeling complex physics, especially things like hydrofracturing, where fluid and solid mechanics are tightly coupled, well, many models get verified.
Meaning they match known analytical solutions.
Exactly. They match the math. But real confidence, particularly for engineers out in the field, that only comes from validation. Proving the model actually predicts the experimental data points. The rock, doesn't care about your simplifying assumptions.
Good point.
And this paper really gets where the rubber meets the road for engineers. Okay, the final fracture path is important, sure, but often the highest stakes data point. It's the time evolution of the fluid pressure right at the wellbore.
Ah, right, the pressure curve.
Precisely. If your simulation can't accurately predict that pressure curve, which dictates, pump requirements, safety limits, all that operational stuff, then the model is, well, it's practically useless in the field.
So this GFM method, it was already verified against simpler cases.
It was, yes. And now it's being systematically validated against these critical experimental metrics. That pressure evolution, the fracture radius over time, and the opening displacement, the stuff that really matters.
Okay, let's unpack this GFM methodology then. What actually makes it different from, say, standard finite element analysis? How is it built to capture this real-world physics?
Well, at its heart, GSM is an advanced numerical tool. It uses the framework of linear elastic fracture mechanics, LEFM, to handle the solid rock deformation. That's fairly standard.
Okay.
But critically, it tackles the coupled problem, the fluid flow inside the growing fracture, using Reynolds lubrication theory.
Yeah.
So it has to model both things happening at once,
Uh-huh.
the rock opening up and the fluid pushing it open.
And doing that in 3D must be computationally intensive.
Hugely intensive. That's the primary challenge. Modeling that sharp crack front requires incredibly fine meshing, especially right at the tip. If you just used a brute force fine mesh everywhere.
You'd be waiting weeks for a result.
Exactly. So GFM uses some clever techniques to get accuracy without that astronomical computational cost. There are really three key things. First, mesh adaptivity. Instead of a uniform, dense mesh, the simulation automatically unrefines the mesh away from the crack and then re-refines it only right around the moving fracture front.
Ah, so it focuses the computing power just where it's needed?
Precisely. At every single propagation step, this saves massive amounts of computational time. It's like focusing a camera lens only on the action.
Smart. Okay, what's the second technique?
Second, they use something called geometrical singular enrichments. These are basically special mathematical functions added into the standard finite element calculations, but only right around the fracture front.
And what do those do?
They allow for a very robust and highly accurate calculation of the stress intensity factors. Those are the parameters that basically tell the crack where to go and how fast if you don't get those right.
Your simulated fracture goes off in the wrong direction.
Completely haywire, yeah. So these enrichments are key for accuracy at the tip.
Okay, adaptive mesh, singular enrichments.
Yeah.
What's third?
And finally, there's an automatic algorithm that computes the time step needed for the simulation. In these dynamic problems, the time steps have to be incredibly small, and they often need to change as the fracture grows to keep things stable and accurate.
So you can't just set one time step and let it run.
No, not efficiently or accurately. Having this adaptive algorithm manage the time evolution is essential to make the model run effectively over the whole experiment duration.
So GFM sounds like a pretty optimized tool then. And the experiments it was tested against, they were specifically designed to push it, right, across different physical regimes.
Absolutely. They wanted to test it against propagation in both toughness-dominated and viscosity-dominated regimes first, using simple geometries, and then move on to more complex non-planar shapes.
Okay, let's talk about those regimes. Toughness versus viscosity.
Right. If you boil hydraulic fracture growth down, you often get these two limiting cases, especially well-studied, using simple planar penny-shaped fractures.
Like a flat disc growing outwards.
Yeah.
Exactly. In the toughness-dominated regime, the main thing controlling the growth is the energy needed to actually break the rock, create new fracture surface area. That's the rock's fracture toughness.
Okay.
Because propagation is relatively easy from a fluid flow perspective, the pressure tends to stay pretty constant across the whole fracture face. Not much pressure dropped from the wellbore to the tip.
Makes sense. And the viscosity dominated.
That's the flip side. Here, the energy loss due to the fluid's viscous drag, how thick or sticky it is, becomes the dominant factor. The fluid really struggles to flow quickly into that narrow crack tip.
So you get a big pressure difference.
A much steeper pressure gradient, yeah. High pressure near the injection point, dropping off significantly towards the crack front.
Okay, let's dig into the experiments. Block 4 was toughness dominated, right? How did GFM do there?
It did stunningly well, actually. The GFM results matched the experimental pressure data exceptionally well, that critical initiation pressure. The relative error was tiny, less than 2%, about 1.94%, I think.
Wow, that's close.
Very close. And it tracked the fracture radius accurately, too. But there was a fascinating observation, something both the experiment and the simulation showed.
Oh, what was that?
Because the pressure is so flat across the fracture in this toughness regime, the fracture center itself doesn't necessarily stay perfectly aligned with the wellbore.
It moves.
It actually translates laterally, slightly. Even while keeping its circular shape, it seems to sort of chase minor weaknesses or instabilities, a path of least resistance kind of thing.
Ah, that's unexpected.
It is a bit counterintuitive. Now, while the pressure and radius match was great, there was a slight mismatch in the fracture opening, about 8 to 11% error.
Any idea why?
The researchers suspect it might be related to that shifting center, or possibly just the inherent difficulty in precisely measuring that tiny crack opening in a physical test using LVDT gauges. Could be measurement noise or influence.
Okay. But there was another critical validation point here, wasn't there? Something about the wellbore.
Yes. This is really interesting. The wellbore system compliance. You have to think about the fluid before the rock actually cracks. It's sitting inside the metal tubing of the wellbore system under high pressure. It's compressed.
Like a loaded spring?
Exactly. And when the fracture suddenly pops open, all that stored elastic energy in the fluid volume is instantly released, surges into the new fracture space.
Ah, so for a moment, the flow rate going into the fracture, let's call it kin, is actually higher than the flow rate from the pump, Q0.
Precisely. It exceeds the pump rate temporarily. This isn't just some minor modeling detail, it's a critical effect. The GFM simulation had to explicitly model this transient compressibility of the fluid in the wellbore system.
And did it match the experiment?
Perfectly. If you ignored this effect, if you just assumed kin equals Q0 right from the start, your prediction of how fast that crack grows in those crucial first moments would be totally wrong. That initial burst of energy is paramount. Matching the pressure profile confirmed GFM captured this transient flow.
That really is a big vote of confidence for the model's practical use. Okay, let's switch gears. PGMY8, the viscosity-dominated experiment. How did it fare there?
Well, as you'd expect, GFM did capture that steep radial pressure variation characteristic of the viscosity regime. The match was strong initially during the pressure buildup, but then things got mysterious. Right after the breakdown pressure was reached the point where the rock actually fractures, the experiment showed this very distinct, sharp jump or overshoot in pressure.
That jump?
Yeah, sudden spike, and then it settles. And interestingly, neither GFM nor the other numerical codes they compared against could replicate that specific jump.
So the models missed something happening right at breakdown.
It strongly suggests the physics immediately following that initial crack formation are more complex than the current models based on LEFM and Reynolds flow are capturing.
Any theories? What could be missing?
Well, it raises important questions. Are we seeing effects like microdamage, maybe some shear dilation near the wellbore that the continuum model doesn't account for? Could it be thermal effects, the high-pressure fluid hitting cooler rock?
Or maybe fluid leak-off.
That's another possibility. Maybe a localized spurt of fluid leak-off right at initiation causes a brief pressure adjustment before things stabilize into the main propagation phase. Whatever the cause, that jump tells us the system is momentarily unstable right after breakdown. It's a big area for future research and potentially model refinement.
Okay, fascinating mystery there. Let's move on to the next level of complexity. Non-planar geometry. Saucer-shaped fractures.
Right. These happen when a fracture propagates near a free surface, like the top of a rock sample or potentially the ground surface in the field. The lack of stress confinement from above causes the fracture to curve upwards towards that surface.
Creating a sort of asymmetrical saucer shape.
Exactly. And the amount it curves is controlled by this dimensionless parameter. They call it chi. Chi. It relates to the lateral confinement stress.
So high chi means?
High chi means strong confinement, less curving. Low chi means less confinement, so the fracture turns upwards more significantly. They tested different levels. Test AB5 had ton-E corler, so maximum turning, while C11 milli1 had A1 the least turning.
And did these experiments behave as expected?
Well, they threw a curveball right away. The physical tests showed this unexpected asymmetry and inclination right from the get-go, a distinctly kinked fracture path starting right at the wellbore.
Not a smooth curve.
No, more like it started off at a slight angle.
Yeah.
The researchers figured this was likely due to, small imperfections in the rock or localized stress concentrations right where the fracture started.
So how did the GFM handle that? Did simulating a perfectly planar start work?
Initially, no. When they ran the GFM simulations assuming a perfectly planar initial notch, the simulated path didn't match the experiment particularly well.
Okay, so what did they do?
This is an important point. To get what they called strong agreement with the overall fracture path for the higher curving tests, AB5 and C6 meter 1, they had to rerun the simulations using an initially kinked notch.
Meaning, they essentially told the simulation how the first bit of the fracture actually went.
Pretty much. They matched the geometry of the first 6 millimeters from the experimental data as the starting condition for the simulation.
That feels a bit non-predictive. If you need to know the first few millimeters of the result to predict the rest.
That's a really sharp observation, and it's a critical point. It suggests that while GF is doing a great job validating the physics of propagation, how the stress and fluid mechanics drive the fracture once it's moving, predicting that very initial path initiation, which is super sensitive to highly localized conditions right at the wellbore, well, that remains a big challenge.
So the model is good for the journey, but predicting the first step depends heavily on knowing the exact starting conditions.
Exactly. It puts the onus on the user, the engineer, to have a really accurate picture of the stress state and geometry right at the perforations or the starting notch. But it does validate the physics governing the growth after that point.
Okay. What about the 3D aspect? Was that important here?
Hugely important, especially in the least turning case, C11 and 101. Remember, that one had high confinement, so it didn't curve upwards much. Instead, it grew outwards until it actually broke right through the sides of the cylindrical rod sample.
A true 3D boundary interaction.
Absolutely. And because the GFM models the entire 3D specimen, including those lateral boundaries, its predicted path followed the experimental one very closely, right up until that side breakthrough.
And how did the other model compare?
They compared it against an older code, or Ribik, which assumes axis symmetry. Basically, it assumes everything is perfectly symmetrical around the wellbore. Because of that assumption, Ribik couldn't properly account for the influence of those specific side boundaries. Its predicted path deviated significantly in the later stages.
So that really highlights the need for a full 3D approach when boundaries matter.
Definitely. Whether it's sample boundaries in the lab, or maybe nearby wells, geological layers, or faults in the field, those 3D effects can be critical.
Got it. Now, there was still some mismatch, right? Even with GFM. Something about the fracture opening.
Yes, across all these saucer-shaped tests, both GFM and Oribic tended to slightly overestimate the fracture opening right at the wellbore compared to the experimental measurements.
And the reason?
The researchers attribute it mainly to that significant lack of axisymmetry observed in the actual experiment, the kinking and wobbling which the models don't fully capture. Plus, measuring that central opening in the lab was tricky. It relied on visual interpolation, not a direct mechanical gauge, adding some uncertainty.
So again, real-world messiness versus idealized simulation.
Pretty much. Even when you match the driving pressure and the overall path reasonably well, getting every local detail perfect is tough when dealing with real rock and experimental limits.
Okay, so that brings us to the final challenge they set up for GFEM, a truly 3D test case.
Yes, this was purpose-designed. They modified the saucer problem setup specifically to create a fully 3D, non-isotropic stress state.
Non-isotropic meaning?
Meaning the stress applied wasn't the same in all horizontal directions. They applied full confinement in the x direction, like the chi in our case. But they applied zero confinement in the perpendicular y direction. So cheer dollars in the way direction.
So maximum confinement one way, minimum confinement the other way. The prediction would be a really warped saucer shape, right? It should curve up rapidly and grow much further in that unconfined E direction.
That was the expected overall outcome, yes.
Yeah.
But the simulation revealed something completely counterintuitive, especially in the initial stages, a real twist in the timing.
What happened?
Get this. The fracture front in the A direction, the side with zero confinement, which you'd think would just take off, actually experienced a momentary arrest. It stopped completely for the first 0.36 seconds of propagation.
Stopped. The unconfined side stopped. How is that possible?
It comes down to the coupled system dynamics. The fracture front propagating in the X direction, the confined side started moving first, and because it was pushing against higher stress, it initially consumed a significant amount of the available fluid energy and elastic energy from the rock very quickly. And since the fluid pressure is essentially shared across the whole fracture front at any given moment, that rapid energy expenditure on the X side momentarily lowered the overall pressure gradient driving the entire crack.
So the pressure dropped just enough.
Just enough that the pressure at the A direction front fell below the critical threshold needed for it to advance against even the minimal resistance there. So it just paused, it arrested, waiting for the pump to build the pressure back up slightly to overcome that temporary barrier.
Wow. That's incredibly subtle interaction.
It really is. And only after that brief pause did the A direction front start propagating again in its preferred low confinement direction.
So did the A direction eventually overtake the X direction?
Yes, but it took time. The simulation showed the confined X direction front actually was longer, for the first 13 seconds or so.
Yeah.
But eventually, yes, the zero consignment A direction front caught up and surpassed it, becoming significantly longer toward the end of the simulation, confirming the overall expected effect of confinement. But only after overcoming that initial unexpected hurdle.
And the fact that GFM captured the non-convex shape, the arrest, the complex timing, that's the key validation here.
Absolutely. This level of complex interaction, this non-intuitive, non-convex front evolution, and the momentary arrest, that's what we could only capture with a simulation methodology that robustly models the full 3D coupled fluid-solid system. It really confirms the power and, frankly, the necessity of something like GFM for tackling potentially complex field scenarios.
So wrapping this up, what's the big takeaway here? We've looked at this GFM simulation method and seen it successfully validated against a whole spectrum of lab experiments. Simple planar fractures, complex non-axisymmetric 3D growth.
And across different physical regimes, toughness and viscosity dominated.
Right, and it consistently matched the key engineering data, especially that crucial fluid pressure evolution and the fracture radius.
Yeah, the GFM methodology, with its smart techniques like the adaptive meshing, the singular enrichments, and importantly, accounting for those real-world factors like well-bore compressibility and the full 3D boundary effects. It's really proven it can capture the relevant physics pretty well.
The main question mark remaining is that post-breakdown pressure jump.
Exactly. That suggests there's still some localized physics right at initiation that might need further investigation or refinement in the models. But overall, the validation is strong.
And that final simulation, the non-isotropic confinement one, that really shows the potential for simulating the kinds of, well, messy conditions you might actually encounter downhole.
It does. And that leads me to a final provocative thought, maybe something for you, the listener, to consider.
Okay.
If simply applying different confinement stresses in two horizontal directions in a clean lab setting can lead to these complex, non-convex fracture fronts and even temporary fracture arrest, what might happen in a real reservoir when you introduce things like pre-existing natural fractures or faults or significant layering?
Things that create much stronger, more localized variations in stress and material properties.
Precisely. Much greater non-isotropic conditions. Could that lead to multiple stops and starts, significant fracture branching, or unexpected reorientations that we're only just beginning to appreciate and model accurately?
Yeah.
That's maybe something to mull over next time you're thinking about optimizing a completion strategy in a complex formation.